Thanks a lot, David. So I'm going to continue the saga of factorization homology. So far, we've mostly talked about factorization homology of EN algebras. Today, I'm just working in dimension one. So the way that works is that if I have an E1 algebra, I can take its factorization homology over some framed one manifold. And I get some object of V. So you can imagine that V is like chain complexes or spectra, something like that. What I'm going to talk about today, so something that's well known, especially in the discrete case, is that a ring, an associative ring, is like a one object linear category, and that persists in the higher categorical setting. So I'll refer to this as factorization homology alpha, and cat of V. This, as I'll explain, is infinity categories enriched in V. And so in the same way, you can consider an E1 algebra as such a thing that has one object. And so what I'll talk about today is an extension, which is called factorization homology beta slash enriched. Enriched is yet more general. So an outline is here. So I'll actually spend quite a bit of time talking about this gadget right here. And then I'll talk about first beta factorization homology, and then more generally V-enriched factorization homology. If there's time, I'll talk a bit about the spectrally enriched case, where we end up with something very interesting on the value of factorization homology over the circle, which is also referred to as topological Hochschild homology, namely a cyclotomic structure. But we'll see how far we get. Okay. So, oh yes, and before I forget, the things that I'll be saying are scattered throughout various papers by these guys as well as myself. If you want to know where some specific thing can be found, I'm happy to tell you that as well. So I want to make one quick reminder before I jump into section one, which is that infinity categories, I'll just write cat for that, can be embedded into simplicial spaces. So by this, I mean infinity categories. By this, I mean spaces, aka infinity groupoids. And this embedding, well, I'll just refer to it as the nerve functor. So this takes an infinity category C to some simplicial space denoted N of C, and its nth level is, well, it's some space. And what space is it? It's the space of Homs of infinity categories, so functors infinity categories between brackets N and C. So brackets N here is just the following poset. And so it's the space of N composable morphisms. And what I want to remind you is that the image satisfies what's called the Siegel condition. So on an object X bullet, on a simplicial space X bullet, this says that for any n greater than or equal to 2, xn has this natural map to x1 fibered over x0 with x1. and this map must be an equivalence. So perhaps that's familiar. Let me use this to make a definition. So X will be, curly X will be a Cartesian symmetric monoidal infinity category, by which I just mean X with the Cartesian product thought of as being symmetric monoidal in that way. And I will, I'll refer to category objects in X. I'll just write cat brackets X for that. And that's going to be a full subcategory of simplicial objects. Simplicial objects in X. Let me just remark, if you're familiar with this story, I'll not talk really about completeness conditions today. So you can think of an infinity category as a category object in spaces. So infinity categories are embed not just into simplicial spaces, but in fact to category objects in spaces. Okay, so that was just a brief review. Now let me talk about that first item, section 1, C MFD VFR sub 1. So this is an infinity category of compact variframed 1 manifolds. So I'm going to take a while to define this infinity category, and I'll try to explain it as I go. And I'm going to define it using the description I just gave of infinity categories in terms of simplicial spaces. So first, let me describe its, so also for simplicity, I'll just write curly M for this. So I don't write that same thing over and over. So the nerve at level 0, this is the space of objects of M. They are the following. They are finite disjoint unions of circles along with finite directed graphs. And I should say that this circle is required to have a framing. And here K is an integer greater than or equal to 0. So an object is called a compact variframed 1 manifold. So I want to just take a moment to explain what this word means, because, well, with an eye towards the higher dimensional story, I think it's useful. These, let me just also say right now, these could also be called stratified. But that's implicit in the word variframed, as I'll describe right now. So let me first recall, if I have a manifold M, a framing of M is the following data. So M is a manifold, in particular a topological space. And I can look at its fundamental infinity groupoid. And well, M carries a canonical vector bundle called its tangent bundle. And that's classified by a morphism of spaces. From its fundamental infinity groupoid to the classifying space BGLN-R. And what a framing is a trivialization of that. So it's a lift, like so. So that's what a framing on a manifold is. So here I'm talking about veriframings, and if M is now a stratified space, and let me just say, I'm very much not going to define this. The higher dimensional the general definition is quite involved. It ends up having really amazing formal properties, but if you want an actual definition, it takes quite a bit. On the other hand, the one-dimensional situation is easy, and so we won't need to worry about it either. So if M is a stratified space, this is in the sense of Ayala Francis Tanaka, a veriframing is, so, well, there's a replacement, first of all, for the fundamental infinity groupoid called exit of M. So this is the exit path infinity category. So its objects are points in M, and its morphism, this is a heuristic description. It's also a subtle technical point to define this. So its objects are points in M, and its morphisms are exiting paths. So in a fundamental infinity groupoid, objects are points, morphisms are paths. Here, now that M is stratified, and I'll just draw an example, is that the exit path infinity groupoid, well, first of all, here's an example of a stratified space. This is a one-dimensional stratified space. So exit takes stratified spaces to infinity categories. And here's its exit path infinity category. Well, it has an object here. So right here, for example, that's an interval, but up to homotopy, an interval is just a point. So there's one object here corresponding to all the points in that interval. The space of them is contractible. And then an exiting path is allowed to go from lower dimension to higher dimension. So let me just complete this picture. So this is an infinity category. It's the disjoint union of that poset and that groupoid, S1. So that is our replacement for the fundamental infinity groupoid. And well, a stratified space, whatever the heck that is, has a tangent, not just a tangent bundle, but a tangent constructible bundle. So this goes to a certain infinity category, vect inj. So that is the infinity category underlying the topological category of real finite dimensional real vector spaces and injections, injective linear maps between them. So what does constructible mean? Constructible means locally constant over each stratum. So just looking down at this stratified space right here, you can imagine what this functor does? Well, it takes, for example, this object, well, that's a zero-dimensional stratum, and it takes it to the tangent space of that stratum, which is just the zero-dimensional vector space. And then on a one-dimensional stratum, it goes to a copy of a one-dimensional vector space, and so on. And so when I say locally constant over each stratum, let me say, namely, Tm restricted to the pth stratum is just the tangent bundle of the pth stratum. What's interesting is the fact that there are morphisms here, these exiting paths, which are carried to injections among real vector spaces in a continuous way. So vect inj, likewise, if I want to trivialize something, a map to it, well, there's this point is sort of picking out, this point up here is picking out a very standard copy of Rn. And here, well, I want to pick out standard copies of all of the vector spaces around. So this is just a poset picking out R0, including standardly into R1, including standardly into R2, etc. And this, finally, is what a veriframing is. So again, a framing is a trivialization of the tangent bundle. A veriframing is a trivialization in this sense of the tangent constructible bundle. Okay, great. So hopefully that is clarifying, suggestive of higher dimensional cases, and also explains this definition a bit. I've got S1s that are required to be framed, and then also finite directed graphs. And what I'm saying is that these are instances of some more general notion of a veriframed stratified space. Okay. So I've described what the objects of this infinity category curly M are, compact veriframed one manifolds. Now let me describe the morphisms. And again, I'm using this perspective on infinity categories as certain simplicial spaces. So a morphism in M, again, that means C, MFD, VFR1, is the data of a diagram of stratified spaces. Again, something that I have not quite defined, but in these low dimensions, it's not so crazy. It's a diagram as follows. It's a stratified space mapping as a proper constructible bundle down to the following stratified space. And let me just finish this before I describe what those are. So this is the zero simplex, including, that's some okay, so sorry, I stopped talking in the middle of that. So this is the standardly stratified one simplex. So first, let me just draw a picture. It's a one simplex. In particular, it's a topological space, but it also has a stratification, and it looks like this. So, or maybe I'll just draw it like that. So that's a closed interval, but there's a stratum here, and then there's a separate stratum here. And what that really is a topological space, namely the topological one simplex, equipped with a continuous map to the poset brackets 1, which again just means the poset 0 less than 1. So that is a stratified space is in particular a topological space equipped with a continuous function to a poset. And this is an example of such a thing. So this right here is the source of the morphism. This right here is the target of the morphism. And let me say that this M, this is a proper constructible bundle, and this has, I'll give some examples in a moment, but let me finish the definition. This is required to be equipped with fiber-wise variframing. When I say fiber-wise, I mean over the standardly stratified 1 simplex. And, well, in particular, this is the fiber over the 0th vertex, and this is the fiber over the 1st vertex. And so we have variframings on M0 and M1 in particular. So indeed, those are objects of this infinity category curly M. Okay, so let me just draw an example here. So here's an example. Okay, so this is my M, and M is supposed to project down to this standardly stratified 1 simplex, which I'll just draw again. It's here and there. So again, this is a constructible. This is a constructible bundle, which means, well, there's 2 strata here. There's the 0 stratum and the 1 stratum. And again, constructible means that it has to restrict over each stratum as just a fiber bundle. So there's some fiber here. This fiber right here, that's M0. And the fiber over here is M1. And then aside from, well, all of the interestingness happens as we exit from 0 to 1. And then once we've gotten out to here, everything is just a fiber bundle over this contractible space, and so there's no data there homotopically. So let me just point out a few features. Let me just add in some more stuff here. So here are things that can happen. We can have this portion of circle splitting apart into multiple pieces of circle. Or here, this edge splits apart into that edge as well as this edge. And then this lower part, you know what, let me change this a little, actually. So notice that this dot disappears. That dot disappears. Notice that it only is allowed to disappear because these 2 one-dimensional strata on either side of it, their framings agree. Whereas this dot could not disappear because the framing here goes up and there goes down. Okay, so yeah, things can be like multiply covered like that, or multiply covered here. Things can be unchanged, like this dot. There's this piece that just continues across that covers this as like a homeomorphism, and so there's a lot that can happen in this infinity category curly M. And let me remark that it's pretty crazy and involved, but in fact, I'll describe, if there's time, a completely algebraic. There exists a completely algebraic characterization of this infinity category curly M, which I may describe if there's time, or if not, I'm happy to describe it offline. Yeah, so as crazy as all of this is, it turns out, and you might think of that as it's of the flavor of the cobordism hypothesis, in a sense that you name some algebraic universal property, and then whatever infinity category that pops out ends up having a description in terms of differential topology. Okay, so I've described a morphism. Let me also describe compositions. And again, I'm spending more time on this partly because this is relevant for the higher dimensional cases, which you can imagine, or perhaps it'll be spoken about later. Two composable morphisms are exactly the data of a constructible bundle lying over this stratified space. This is not great, but that's okay. Okay, so this is, let's say, oriented up, and then, yeah, so everything's oriented up here. There are a few things happening. So first, in the first morphism, which is depicted here, there's one sheet where this dot, everything here just kind of like stays without anything happening to it. This dot persists, but then also there's just the lower half, the lower interval splits apart and has another piece coming out right here. And then in the second morphism, up here we see that this dot disappears. Meanwhile, this interval splits apart into two intervals. And I need to describe for you a way of composing, which is to say, I take these two composable morphisms and I name for you a single morphism. And the output looks like this. So on the one hand, there's this one upper sheet that's oriented like that. And then also there's these two lower sheets that split apart. The point here is that there's some sort of functorial resolutions that are happening. For example, this path right, this edge right here just kind of got slurped into the zeroth portion, to the fiber over the zeroth vertex. Meanwhile, this splitting that only occurred after a while somehow canonically the splitting gets pushed all the way back to being split at the zeroth vertex. So let me give you the real definition. I'll tell you what is the space of n composable morphisms in this infinity category, curly M. it's the space of proper constructible bundles of stratified spaces over, well, the standardly stratified N simplex. I'll just draw an example in a second, with fiber-wise variframings, such that all fibers have dimension less than or equal to 1. So there's some space of these, and that is this space that I want to describe, that is being defined to be the space of n composable morphisms here. So delta 2 standard, you could draw it like this. So there's a stratum, and then there's one last stratum like this. So again, this is a stratified space. In particular, it's a topological space equipped with a continuous function to a poset. And hopefully this picture right here is suggestive of what function I mean to indicate. So keep this in mind. We've got this, and this. In particular, let me point out, there's sort of like a 2-1 horn inside of here, which is like this and that and that. And the 2-1 horn is exactly this thing right here that I just drew. And then this right here is the long edge of the 2 simplex. So the assertion that this defines an infinity category in particular is the assertion that the space of such bundles over the standardly stratified 2 simplex, well, there's this forgetful map to the space of compatible pairs of 1 morphisms. And part of the assertion is that that map is an equivalence of spaces. So that is really what I meant when I said functorial resolutions, is that given any such picture like that, which is to say something, any constructible bundle over this orange horn, which is to say some sort of data like up here, that's a point downstairs, and this is an equivalence of spaces, so there's a unique point up to contractible choices up above that restricts to it. In other words, there's a unique extension. So that extension is this functorial resolution. Okay, maybe this is a good time to pause and see if there are any questions. Or maybe, well, people should feel free to jump in at any time. Okay, I'll just continue. So I just want to highlight 2 main constructions of morphisms in this infinity category curly M. So one of them is what I'll call a reversed cylinder of a proper constructible bundle of stratified spaces. Let me just draw a picture and leave it at that. So here you can see, you can imagine that this came from some proper constructible bundle among stratified spaces. Here's one, here's the source of it, and here's the target of it. So you see the circle projecting onto a point, and this edge projecting onto that piece right here. So that's one construction. And another construction is just the like forwards cylinder of a refinement morphism between stratified spaces, which is just a homeomorphism on underlying topological spaces. So like, for example, there's a picture of a constructible bundle over the standardly stratified 1 simplex, which depicts a refinement of this circle with 2 dots on it to this circle with 1 dot. And you can see that the morphism actually records for us which dot was kept and which dot was not. So there are refinement morphisms, and they come from homeomorphisms on underlying topological spaces. So in a sense, these generate all possible morphisms in curly M in a precise sense. And something that is subtle, so this infinity category was tailor-made for factorization homology. And the reason that this is difficult is that on the one hand, factorization homology has backwards functoriality for these proper constructible bundles, but it also wants to have forwards functoriality for refinements. And so that is what leads to this definition. Okay, so let's start talking about the best one manifold there is, which is the circle. So inside of this infinity category curly M, there's an object called S1.
Hey, Aaron, I had a quick question before you went on, if you don't mind me interrupting.
Yeah, please.
Yeah, it's Mark Penny. Is there a sense in which this category is generated by these 2 classes of morphisms?
Yes, yes. So let me just depict. There is, first of all, for any morphism, there's a closed active factorization. So these mimic the notions of closed and active and perhaps inert, also known as for like infinity operads. And there's always a unique such factorization. On the other hand, any active morphism can be factored non-uniquely as a creation morphism followed by a refinement morphism. So refinement morphism is this type, and closed and creation are of these type, depending on whether the constructible bundle is injective or surjective. So in particular, if there's no refinement going on, then this is just a massive enhancement of the usual factorization of just like, say, a function of sets as an injection followed by a surjection.
Okay, interesting, thanks.
Yeah. Yeah, you're welcome. So I want to study.
Sorry, could I interrupt briefly? This is Jay.
Hey, Jay. Yeah, sure.
Yeah, maybe piggybacking off of Mark's question, are there any familiar subcategories of this category M that we should be aware of?
Well, that's what I'm about to describe now. But also, let me just say that there are more pedestrianly defined infinity categories of stratified spaces. Say, so for example, there's an infinity category of stratified spaces and constructible bundles being the morphisms between them, and then there's also veriframings on everything that are compatible. And there, so part of what I'm saying as number 1 is that there is an embedding, which in fact is surjective, let me say also one-dimensional, into this infinity category M, which, just to emphasize, is like that. So among the morphisms well, all of the objects are such things, but then among the morphisms, it's a condition for a morphism to come from here, which is really a subtle point, but it's super important. So there's a lot of technical work in the background here at the interface of higher algebra and differential topology. There's likewise what's going on with this lower one, as long as I've said it, strat ref VFR 1. So this is this reversed cylinder construction, and there's this open cylinder construction, and that's a covariant functor. So again, the complication of M is the fact that it mixes forwards and backwards maps.
Thanks.
Sure. So I've got this object, the circle, and I want to describe what it generates. So first of all, it has a full subgroupoid that it generates, and hopefully it's believable that all that the space of equivalences from the circle to itself is actually the circle group. They're all just framed diffeomorphisms. But we can go further. We can look at the full subcategory generated by the circle, and this is BW, I'll call it. I'll describe it in a moment. So this is fully faithful. This thing right here is called the Witt monoid in the sense of the Witt vectors. So in the context of topological Hochschild homology, this is sort of keeping track of like Frobenius and Verschiebung, that sort of thing. So a morphism in T, that's just like an equivalence, a framed diffeomorphism between framed circles. In BW, a typical morphism, so I mean, both of these only have one equivalence class of object, but a typical morphism here is actually going to be one of these reversed cylinders. It has no choice but to be some sort of covering map, the opposite of a covering map between framed circles. So this is like an R-to-1 covering map. In particular, there's actually a degree function. Any such covering map, you can just ask what its degree is. And so it projects, well, the degree is always a positive natural number. And degrees are multiplicative, so I'll write Bn cross. So n cross is a monoid. And there's this degree function. And well, look, the morphisms of degree 1 are exactly the equivalences. So in fact, this is a pullback right here. And that pullback witnesses W, this Witt monoid, as the semi-direct product of n cross acting on the circle group. So the circle group has all these interesting endomorphisms as an infinity group, like Z goes to Z to the R, and that's the endomorphism that the natural number R is carried to under this action. So this will recur for us later. Okay, so also inside of this infinity category M is a subcategory which is much easier. It's the subcategory of disk stratified compact variframed one manifolds. So C MFD VFR 1, it has this subcategory C disk, same decorations. So this I'm just calling M. This I'll just call curly D. So it's just full on those without any unstratified circles. So you're just not allowed to have any smooth circles. In other words, the objects of curly D are just finite directed graphs. But the morphisms are still interesting. It's this, it's a full subcategory after all. So that allows me to make a following definition. For any object M in curly M, of course, you should be thinking about the circle here. It's infinity category of disk stratifications. And this is going to be useful for factorization homology. It's so curly D of M, which is just by definition the refinement morphisms from objects of D. So by definition, this is a subcategory of this fiber product. So it's an object of curly D, considered as an object of curly M, equipped with a map to M, and then that map is required to be a refinement. So let me do the example. M equals S1. So then the objects, by which I mean the unframed smooth circle, so the objects are refinement morphisms to the circle from disk stratified things, which means I must put at least one dot on the circle. I'll put 3. And then I have a morphism to the smooth circle. And well, this is framed. And so note that actually all of these must have compatible framings as well. And I'll just write the source here. I mean, there's not much data in the morphism itself. So a morphism in, so this is, I'm describing D of S1. A morphism in D of S1, let me just draw an interesting one. It's going to be from a circle with 3 dots, 4 dots, to a circle with 3 dots. Okay, so I'll stop drawing the framings. They're always going to have to go the same way because remember, these are refinements of the smooth circle, so they have no choice but to have their framings. I'll draw it in gray so you can know that those are going away soon as I continue to talk. The framings must all go in the same way because they are required to agree with that of the unstratified circle in the sense that they refine to it. So what is going on here? Well, first of all, their dots can disappear. And this is an instance of this refinement that I was referring to. Dots can also anti-collide. So a disappearance of dots just by itself corresponds, remember, to a forwards morphism on stratified spaces. An anti-collision of dots is one of these creation morphisms. So for instance, right here, here we see an anti-collision. That dot is splitting apart. And somehow this interval is projecting down onto just that dot right there. Of course, this morphism that I've depicted is a composite of other more fundamental morphisms coming from basic geometric, like ordinary morphisms between stratified spaces. And then let me just emphasize that you can also have isotopy. So that's what's responsible for this sort of Dane twist type phenomenon that you're seeing here. So just to ground us, let me observe that the space of objects of D of S1, which is, after all, just the zeroth level of the nerve, it is a disjoint union of configuration spaces of points in the circle. So hopefully that should be plausible. After all, oops, not 0, but rather 1. I've described the objects, and I've described the objects like this. You have to have at least one dot, and then equivalences between them, which is all I'm describing here. All that can happen is that the dots slide around. So that's exactly the configuration space. Okay, so here's a fact, is that this construction D of is functorial for, first of all, equivalences in M, and in fact, more generally, contravariantly functorial for covering maps. So let's return to this composite that we had before, ET mapping W. So I had D of S1 up here. The first thing I want to say is that this can actually be identified with something totally combinatorial. This is called the paracyclic indexing category. So if you've seen this defined elsewhere in a combinatorial fashion, the theorem is that this infinity category, which is defined in terms of differential topology, is actually equivalent to that combinatorially defined category. So the functoriality for equivalences means that this actually carries an action of the circle group, and it's the pullback of a bundle over BT, and that is nothing other than the cyclic indexing category. So this is the cyclic indexing category, and just by construction, this thing is the quotient of the paracyclic category by its circle action. So that's the cyclic indexing category. But even better than that, because this is contravariantly functorial for covering maps, W acts on the paracyclic category, and the same construction essentially gives us the epicyclic indexing category. So that looks like this. And so by definition, this is the paracyclic category where you take the homotopy quotient, actually a lax quotient by the W action. So a typical morphism in here is going to look like a morphism in BW, but then also with stratifications, disk stratifications everywhere. So perhaps there's a dot, and then maybe it splits apart right here. So this dot, right at the, as we go from the zero fiber forwards, things split apart. So this dot is actually splitting out into 3. These two are sort of following each other and going to one portion of the circle, and that one is coming to this other portion of the circle. So there's some interesting interaction between the covering map between circles and then where the dots are allowed to move. So that's the epicyclic category. Here's a remark as well. So there's a standard functor from the simplicial category to the paracyclic category. And this functor is a final functor, which means that colimits over either of them are the same. And so this I've described as disk stratifications over S1. And let me just say that there's a way of identifying this as something else. So this is like relative disk stratifications. So it's disk stratifications of the circle relative to some fixed disk stratification. So rather than define it precisely, let me just indicate there's like some dot that's very fixed that you're never allowed to move. It's never allowed to disappear or anti-collide. And as a result, that kills off all of the automorphisms of the circle. So the standard cyclic bar construction for Hochschild homology is defined as some simplicial thing. And as we'll see, it's actually coming from something better, which does have symmetries. One last remark before we go to factorization homology is that there's a functor. This is totally unrelated. There's another functor from delta op into D called cellular realization. And that just takes brackets n to a picture like this with n intervals. And this is fully faithful. So in the one-dimensional case, that's easy, but it's much subtler in higher dimensions. Okay, so let me tell you about factorization homology. So first, just recall that, so if X is Cartesian symmetric monoidal, we have this cat of X, the category objects. For example, Infiniti categories are category objects in spaces. So here's the definition. Cartesian factorization homology beta is the following composite. So you take your category object, for instance, an ordinary Infiniti category. You take your category object. So first of all, just consider it as a simplicial object. And now, first, you can take the right con extension along that cellular realization functor. So that gives us a functor from D into X. And then you can take left con. I'll describe what all is going on here in a second. Left con extension along the standard inclusion from D to M. And that gives us a functor from M into X. So notationally, this takes a category object and gives us the functor that sends a compact bareframed one manifold to the factorization homology of C over it. So that's the notation. And again, mostly you should just think of X being spaces, and then you're getting factorization homology beta, as I indicated earlier. Let me just say verbally that this composite is fully faithful, and it's a sort of variant of this that is used in the proof of the cobordism hypothesis that's sketched in the archive paper of David and John. So let me describe what this does. Here's what is actually a pretty hard lemma, is that for a disk stratified one manifold, the factorization homology over it, which is, well, this functor is fully faithful, this last functor is fully faithful. So this factorization homology is really just R-con of C evaluated at D. Let me say this is as expected. For example, if D is the following disk stratified one manifold, then the factorization homology over D of some category object C is just a limit over the ways of labeling the edges by morphisms and the vertices by objects. So the source and target morphisms look like that because of the orientation in that direction. Okay, I'll not finish this. There's a disjoint copy of C0 right here. That was what I was trying to indicate with this dot right here. All in all, if you're just labeling a disk stratified thing, if you're taking factorization homology of a disk stratified object, then you're just labeling its edges by its dots by objects and its edges by morphisms. So what that means is, or well, that allows me to describe better the factorization homology over an arbitrary object. For instance, the circle. The factorization homology over M of this category object C, well, just by definition, as a left Kahn extension like this, it's the colimit over all possible maps from objects of D into this M. So this is this fiber product. And then, well, you forget the map to M and you apply this functor of factorization homology just defined on D into X. So up above here, this hard lemma helps us describe this functor. And that's very helpful. But note that this source Infiniti category is still pretty large. And so there's another key lemma here. So remember, I defined this Infiniti category of disk stratifications of M. And another key lemma, though not nearly as difficult, is that this functor is final, which means that colimit is just equivalent to a colimit over some composite like this, where if we have some refinement of M, you forget the map to M and you just remember D, and then we get the factorization homology over D. So ultimately, factorization homology beta in dimension 1 is this colimit over the disk refinements. So again, that's just like ways of putting dots on M. And then those dots are allowed to isotope, anti-collide, and disappear so long as they don't leave us with unstratified circles. And then you decorate each of those things by C, meaning you decorate its vertices by objects of C and its edges by morphisms. So there's a kind of nice, there's a nice interplay here which is that this D of M construction is not entirely functorial in M. So this left con extension description gives functoriality of the factorization homology of C. Remember, it was defined as a functor from category objects to functors out of M. On the other hand, this reduction to D of M gives, I'll say, computability. And returning to the case of factorization homology over the circle, because of that finality that I stated earlier, there's this final functor, so you can restrict further. This is disk stratifications of the circle. And this composite functor is nothing other than the familiar cyclic bar construction. If you've seen a different definition of Hochschild homology, of either a category or an algebra, you could define it this way as factorization homology over the circle, and the usual definition uses the simplicial indexing category and the cyclic bar construction and its colimit, but this is a definition that is more tied to the geometry of the circle, and in particular keeps track of the functoriality, such as the circle action, just for free. Okay, so so now I'll talk about factorization homology of enriched Infiniti 1 categories. So the first thing I need to tell you is what is an enriched Infiniti 1 category. So let me start out with a prior definition. For V, I'll just write box times for an abstract monoidal structure. So we have its bar construction. I'll write that as BV. So this is a simplicial object in Infiniti categories. What does that record? Well, at level 0, it's just a point. At level 1, it's V. And then this simplicial structure map picks out the unit object. And then at level 2, we have V squared. So there's a projection, tensor product, a different projection, etc. So this is essentially its non-symmetric infinity operator, if you're familiar with that language. Let me observe for future use that this BV is actually a category object in Infiniti categories. And this is going to be the reason that I used just an arbitrary Cartesian symmetric monoidal X earlier. So here's one other definition of a category object in CAT. Given a space X, the codiscrete category object on X is, right, CD of X. And let me just draw the simplicial diagram. It's X in degree 0 x squared in degree 1, x to the third in degree 2, and so on. So these are both projection maps. This is the diagonal, and similarly all the way up. So this is in fact a category object in spaces. As such, it can be considered as a category object in infinity categories. And as a category object in spaces, you can think of it, its space of objects is X, and then for its morphisms, for any 2 points in X, I have to tell you what the morphisms are, and the Homs are contractible. Oops, uh-oh. The Homs are contractible. So, you know, there's a classical construction. If you have a set, you can construct a category out of it, which is like a contractible category, and there's one isomorphism from every point to every other point. This is the exact same thing, only for infinity groupoids rather than zero groupoids. Okay, so now here is a definition, and this is due to and has been extensively developed by David Gepner and Rune Haugsang. A V-enriched infinity category is the following data. First of all, its space of objects, I'll call this C. Its space of objects, I'll just call that X, along with a lax functor of category objects in cat. So it's a lax functor, which I'll describe, which runs like this: CD of X mapping to that category object. And this lax functor is called Hom of C. So let's unpack what this could mean. Well, I'll just describe it in the lowest dimensional cases. So this is stuff in delta op. I've got the object 0. I put that little circle to remind myself it's actually in the opposite category. There's the object 1, and there's the object 2. So there's an interesting morphism from 0 to 1. That's a degeneracy. And then there's also a face map from 2 to 1. So let's unpack what this lax functor, if you like, right lax functor, there's a handedness there, what it does. So first, let me just describe what these are. Point V and V squared. So this, as I described a moment ago, is the diagonal map. This is the projection onto the 0 and 2 pieces. Meanwhile, this selects out the unit object of this monoidal category, while this is the tensor product functor. So let me describe this Hom, what it's doing. Well, from on level 0, there's nothing to describe. It's X going to a point, and there's exactly one such map. More interestingly, let me make myself a little more space here. So more interestingly, at level 1, I've got this functor from X squared to V, and what does that do? Well, it takes a little x and a little y to the object of V called enriched Hom in C, the V-enriched infinity category that I'm attempting to define, that I'm in the process of defining from X to Y. So again, X is the space of objects. So for each pair of objects, I should be defining an object of V. And then up here, what's happening, or down here, what's happening is that I take a triple X, Y, Z. So I'll just write this as brackets X, Y for short as I get lazy. So this triple is supposed to go to a pair of objects in V. And the objects that those are, well, one of them is the Homs in C from X to Y, and the other one is the Homs in C from Y to Z. Okay, so that is the level by level data. But then this is not supposed to commute, rather it's right lax. So the directionality ends up meaning that there's a morphism this way, first of all. What does that mean? Well, for each point in the space X, I'm supposed to name a morphism. So if I go around the top and then down, well, it goes to the only point in point, and then that selects out the unit object. Meanwhile, if I go down and then across, I'm getting the enriched Hom object from little x to itself. And I'm getting a map here. That's what the data of that natural transformation is. And of course, that's the unit, the enriched unit for this object of this enriched infinity category. On the other hand, if I have a triple x, y, z, this natural transformation goes this way. And what that's going to be sent to is if you go across and then down, you're taking Homs from X to Y tensored with Homs from Y to Z. And then that maps to Homs from X to Z. And of course, that's composition. So that is the data of a V-enriched infinity category. Okay, so now I can describe for you enriched factorization homology. Let me first just say the slogan is enriched factorization homology via categorified factorization homology. So now is when I'll use that factorization homology beta Cartesian that I described a moment ago. So here's the definition. If V is not just monoidal, but symmetric monoidal, I'll describe why that's necessary in a moment. The V-enriched factorization, and C is a V-enriched infinity category, which I was denoting as cat parentheses V rather than square brackets. The V-enriched factorization homology over M, M is one of these compact variframed one manifolds. It's the following colimit. So what I'm going to do is take this categorified factorization homology over the infinity category of disk stratifications of M. So I'll explain why this makes sense in a moment. So I have these category objects, CD of X, CD of X, and also BV. Okay, so these two objects are bundles of categories over D of M. So I'm going to explain this definition. So D of M, a typical object, if M is the circle, let's say, is going to be like a circle with some dots on it and framings on the one-dimensional strata. Now this is a bundle of categories that assembles the factorization homology over a disk stratified one manifold D for all D in D of M. So the typical a typical object in the fiber over this circle with three dots. On this side, well, it's going to be the same circle, but now I have to take the factorization homology of CD of X. And what is that? Well, remember, it's this category object that only has interesting data at the level of objects. It has the space of objects X, but then there's exactly one morphism between any 2 points in X. So this is nothing other than X0, X1, X2, and there's just unique possible choices for the one-dimensional strata, because there's exactly one morphism between any two objects in that category object CD of X. And where does that go? Well, it goes to an object in the factorization homology of BV, which is sort of orthogonal in the sense that it had its space of object, its category of objects is exactly a point. So there's nothing to label at the vertices, and I'm supposed to put an object of V over each interval. And well, what do I do? This functor is induced by Homs in C. And so this thing that I'm describing, it goes to Homs in C. So I'm reading off the Hom from the source vertex to the target vertex, from X0 to X1, Homs in C from X1 to X2, and Homs in C from X2 to X0. So that's this red functor. And now I said that I need to assume that V is symmetric monoidal. And the reason is so that this functor exists. Because what is a typical object over here? Well, it's a circle with some dots on it. And then the edges are labeled by objects of V. I, J, K. And I'm supposed to send this to a single object of V. I want to tensor them all together. But these objects don't come with a priorly defined linear order, which is what's necessary to tensor objects in a monoidal category. And so instead, I assume that it's symmetric monoidal. And that way, I have the ability to tensor them together without any ambiguity whatsoever. So actually, by definition, in the case that M is the circle, by definition, you could have it being just what you might call paracyclically monoidal, which sits somewhere between E1 and E2. So it suffices for V to be E2 monoidal in order for this to exist, and it's somewhat stronger than being E1 monoidal, which means that you have tensor product for linearly ordered objects. So let's look at this entire thing. What are we taking? We're taking the category of all objects of here, which are, first of all, a disk stratification of M, equipped with a labeling of its vertices by objects of C, that is points of big X, and then going all the way across, we send it to the tensor product I guess in this case Z mod 3, from xi to xi plus 1, till we send it to the big tensor product of all of those. And when a dot disappears, the Homs are composed. When a dot splits apart, we insert the unit, the identity element of the Hom for the two adjacent vertices that just appeared. They're now labeled by the same object. And this is the factorization homology, the enriched factorization homology of C over M. Okay, so I guess in the last few minutes, I'll describe what's going on with this cyclotomic structure in the spectral case. Unless there are any questions. Okay, so in the spaces enriched case, first of all, in a way that I won't describe for lack of time, in every case, there's a T action on this factorization homology. And that's just basically by the functoriality for framed diffeomorphisms. For the spaces enriched case, this extends to a W action. Let me emphasize that this is spaces Cartesian symmetric monoidal. And so what's going on here is that for any spaces V1 up through Vk, what's happening, so the W action is coming from, remember, covering maps. So given a co-cycle for the Hochschild homology down here, V1, well, really it's going to be Homs, but it's just, Homs can be any object of the enriching category V. I want to repeat I want to repeat the same objects labelings for the vertices, and I want to repeat the Homs, relabel the edges by the same Homs. And what that amounts to requiring is that, well, we have this diagonal map. So if this is an R-fold covering of circles, it's requiring this diagonal map. And let me point out that that actually is equivariant for the CR action. Basically, CR is the deck group of this covering map. So there's a factorization. And this is specifically because the abstract tensor product is just the Cartesian product. That's why we have these diagonal maps. And in the spectrally enriched case, you can attempt to mimic this in the simplest possible way. And you'll see that you don't have diagonals, but the reason that you don't is controlled. So let me just talk about a single spectrum. So you'd perhaps want to have a diagonal map to its R-fold tensor power, that being the monoidal structure there. That does not exist in general. In particular, there is no CR equivariant diagonal map. However, you can quotient out by the reason that there is not. That quotient operation gives you what's called the proper Tate construction. And there is a diagonal map going down like that. And those induce cyclotomic structure maps. So if I have got like two different circles, I can take the factorization homology over 1. This is spectrally enriched. And I get a map to the factorization homology over the other. Oops. With this proper Tate construction intervening. Okay. I'll stop there. Thanks a lot for listening.